Alright, so let's go to the second part of this lecture. We're going to look at some basic terminologies, and then we're going to look at what do we mean by attack, what do we mean by having attack in a multi-class situation, and then we're going to look at what is the three optimization forms of attack, and then we want to look at the objective function, also the constraint set of adversarial attack. So my purpose of going through these materials is to set up a common ground of all the adversarial attacks that you are seeing in the literature. Now, if you could just flip a paper and then you try to read them and then you want to understand what is going on, you will be able, you'll find there are a lot of different types of attacks, and they're written in all kinds of different languages. Even in the surveys, papers that you have seen in the past couple of years, for different attacks, they just have a different equation. The reason I'm introducing this basic terminologies is to try to set a common principle behind these attacks. Eventually, what you will be able to see is that we are going to put all the available attacks under an optimization framework, which by looking at different perspectives of the optimization, you will get different types of attacks. And these attacks, it will be limited to linear models, as we're going to see in this lecture. However, it will be also generalized to deep neural network type of models. And we're going to see how we can do this kind of approximation and generalization in the coming two lectures. So let's begin our discussion of what do we mean by adversarial attack. To define adversarial attack, I'm going to first pick a data point, x0. So I'm assuming that x0 is a d-dimensional data point that belongs to certain class of C of I. Okay, where I stands for the input class, and then I have this data point x0, and then I have a class Ci, and then I want to define a thing called a target class C of T. So what do I mean? Well, I mean that I want to send the data point x0, which is originally in Ci, I want to send it to a target class Ct. Now I'm going to define something called the additive adversarial attack. Now I want to emphasize this term additive because it's a very, very narrowly defined attack mechanism. But this is very typical and very common in the literature nowadays. So what do I mean by the additive adversarial attack? It is an addition of a perturbation R in RD. Okay, and so what is it? Well, it has to be an addition. So now you can look at this equation. Originally you have x0, but now you have x0 plus R. So when you have this x0 plus xr, what happens to the geometry is the following. You will have a data point x0 here. This is your input data point. You are going to move along this trajectory with a perturbation vector of R, and then you go into x0 plus R. And now originally you can see that the x0 is living in the space of Ci, and after this perturbation you go to x0 plus R, and then what is this class? Well, the class becomes C of T. And so adversarial attack, this additive adversarial attack, means that I'm going to add to your original data point x0 in such a way that you will go from one class to another class. This is what we mean by additive adversarial attack. Now, for all the examples that you have seen in the first part of this lecture, they are additive adversarial attacks. For example, the FGSM example, the very beginning example, where you have a panda image, you add some noise pattern, it becomes a gibbon. That was additive attack. For the patch example, you have an image, you change certain pixels to a patch, and then you can attack it. That's also additive attack. The stop sign is additive attack because you have a stop sign and you change the pixel value. That's additive attack. Okay, and so for most of the attacks that you are seeing nowadays, they are additive attack. However, I want to also bring your attention to a type of attack that is more general, that is not necessarily an additive type of attack. This is what I called a general adversarial attack. Okay? Now, what is general adversarial attack? Instead of just using a addition of a vector R, I'm going to define a mapping A that is mapping from RD to RD. So here, if you look at this equation, I have x equals to A of x0. So x0 is your input data. By applying a mapping, I can turn x0 into another vector x. Now this A can be anything. It can be as general as whatever transformation you can think of. Now of course, the additive attack is one type of this A transformation. It's just adding the pattern. Now you can also do a geometric warping of the image, for example, like this one. So this is a paper that was published in WACV 2019. What they do is that they start with an image. This is the correct image. And then they are going to perturb the image using a geometric warping. So you can imagine that there's a face and then you warp the image. For example, the mouth, the nose, the eye. You move things up and down, left and right a little bit. So this is called a geometric warping like this. Okay, so the red dot and green dots means that the flow vector, we call it optical flow vector or the motion vector of how you're going to perturb the pixel. So they move the pixel around and then they can change this image into another image. And so now visually they don't look quite different. However, when you apply the classifier to classify these two images, they become two completely different classes. So when you go back to here, you realize that this general adversarial attack is really, really general. You can have any mapping A that can map x0 to x. Okay, so in terms of this geometry, you can have a completely different trajectory. It's not necessarily just adding from one point to another. That you can transform from one point to another point. Alright, so after we have defined the meaning of adversarial attack, we are going to also look at the problem of multi-class classification, a very, very classical topic that should be discussed way early on, but we didn't have time to talk about this multi-class problem. So the reason to introduce multi-class problem here is that when you think about a classification method, normally you will have multiple classes of objects. It's not just two classes. So when you have multiple classes of objects, how to determine whether you have been classified correctly or wrong? So here we have different approaches to do the multi-class classification. So I'm going to introduce 3 different approaches, and then we're going to stick to one of those as we're moving forward for the remainder of our course. The first approach in multi-class classification is called a one-on-one classification. So what does it mean? Well, you're looking at class I versus class J. So let's say in this case, I have a classification boundary of H23, and then let's say I have a data point here that I want to compare whether this data point should belong to class 1, class 2, or class 3. But since this is a one-on-one comparison, I will only compare using this decision boundary. And in this case, I will say that if I'm compared with H23, then certainly I'm on this right-hand side of this line, and so I will belong to C2 and not C3. But how do we determine whether it is belong to C2 or C1? And then you need to look at this another line. Okay, so for example, this line. So now, because you're looking at the same point here, and then if you look at this line, then you ask whether I should belong to class 1 or class 3, and clearly it belongs to class 3. Okay, because this line is a separating hyperplane across class 1 and class 3. So this is called H13, and so this point belongs to here. And so you say that if I'm using class 1-3, then class 3 wins. And if you look at this case as class 2 wins, and also you can look at this curve, then you can show that it's class 2 win. Then once you do that, you can make a majority vote. So the majority vote, we say is that if you have a data point here, you have two, you use these two, you have three classifiers, and then the two of them will say that it belongs to class C2, and therefore you will say C2 is the class of this data point, which in this case it makes a lot of sense. Now, the limitation of this one-to-one comparison is that you will have a region that is undetermined, which is in the region that sits in the middle. This is an undetermined region because for any pair of these lines, you will find C1, C2, and C3, and so it will become undetermined. Okay? So one-on-one comparison can be used. It's a good thing to use because essentially what you're doing is that you're only doing a binary classification. And once you have the different binary classifications, the decision is based on the majority vote, and that should be quite easy. Now, the drawback makes people to think that would there be alternative approaches other than one-on-one so that you can also handle the areas in the middle. But before we talk about the solution here, let me also introduce another type of approach. It's called the approach 2. This is one-to-all comparison. So what they do is that you're comparing class I versus not class I. Let me give you an example. Let's say you have a data point that's sitting here. Then you're looking at, you want to see whether it belongs to class C1 or not. So you're going to look at this line, and this line is the classifier for C1 compared to anything else that is not C1. Okay, so if you look at this point says that it's C1 and it's not C2 and it's not C3. Okay, so it is one versus all. And then you can also draw the other lines. So for example, you can draw this line, you can draw this line. So among all these lines, then you can determine the regions where it will be classified as C1, C2, and C3. Now the problem of this one versus all approach is that you will have regions that it is undetermined. So these regions, they are undetermined also for this one. Okay. Now you may ask, okay, then why should we consider one versus all? Well, one versus all is useful if you only want to determine whether your data point belongs to one class and not anyone else. You only care about the class that you belong to. So that has certain advantage here, which can tell you this kind of information. But the drawback is you can see that if you do one versus all, you will have a lot of undetermined regions which you are not able to tell which class that the data point should belong to. So in the machine learning literature, what people have been using so far, at least in the recent 10 years, we have been mostly interested in the classification of type like this. Okay? Now in the linear case, it's called the linear machine. What it means is that you're going to partition the space into segments. So let's say this is your classification space. You're going to partition them into 3 segments, 1, 2, and 3 in this example. And then the 1, 2, and 3, they're not overlapping, and then the union of the 3 will comprise the entire input space. So let's look at this case here, that you have class 1, class 2, and class 3. When you define your classifier H12, H13, H23, you are designing the classifiers in such a way that they are not overlapping, and then the union will form the entire space. Now, of course, the price that you need to pay in the linear machine setting is that these classifiers, they are not as simple as the 2 cases before. The 2 cases before, the classifier, they're quite easy to construct. You use, let's say you use one-to-one. What you do is that you just look at one data point and then compare to another class. It's a pairwise comparison. So for any 2 classes, you can do a binary classification, and that's very easy. For one-to-all classification, that's also not hard because you're comparing yes versus not yes. You're comparing whether this belongs to your class versus the complement not belong to a class. So essentially, that's still a binary classification. For this multi-class classification, what you really need to check is not just a binary decision. what you need to check is the discriminant function. If you remember that the discriminant function between two classes is you want to make sure that gi is bigger than gj for all I that is not equal to j. Okay, so this equation is very, very important. It says that you give me a data point. Let's say the data point x is here. This is my data point x. And then I'm going to compute my discriminant function. I apply g1 here. Okay, so let's say I apply g1 to this point. The discriminant value of this data point at this region has to be higher than the discriminant function evaluated at other regions. So if you apply, if for the same, you apply g2 of x on the same, for this data point here, you apply g2, it's going to give you a lower value because you can imagine that let's say you're doing Gaussian, right? So let's say here are the Gaussians, and then since this point is closer to C1, of course C1 will have a higher probability than C2 if you draw a Gaussian there. Okay, and so you want this g1 of x has to be bigger than g2 of x and also g3 of x in this three-case example. And therefore, when you try to construct the decision boundary is no longer a number of lines. It will be a line that has this segment behavior. So this is what we call the linear machine. The linear machine, it is a much more complicated classification scheme. However, it does resolve all the complications that you have seen here, where you have undetermined regions, in one-to-all one and one-to-all classification problems. So for the remaining of this lecture and for the remaining of this entire course, what we are going to do is that we are going to focus on this multi-class problem so that we do not have this, this undetermined region problem. And for this multi-class problem, we are going to imagine that we have multiple classes of data points. There's no overlap. And then if I want to go from one class, let's say I want to go from one class to another class, I will be able to travel to that class and I won't get stuck in an undetermined region. Okay, so let me also comment on this classification, linear machine classification. In this linear machine classification, to look at this equation again, it says that gi has to be bigger than gj for all j that is not the same as I. Okay, now if this happens, then we say that x will belong to class I. Now, if you write down all these equations out, because how many equations I have? Well, I have all the k equations. K is the number of classes. Okay, so let's say k is the number of classes. Then how many equations will I have? Well, you will have a set of equations like these. These equations comes from the fact that you want to make sure that, for example, you are at class I, and then you compare to all the j's that are not the same as your I. Now you ask how many j's are there? Well, there will be k of them because k is the number of classes. So you have g1 compared to gi, that has to be less than or equal to 0, g2, g3, all the way to gk. Now, gi, of course, is included, but that's okay because it's strictly equal to 0. For the rest, you want them to be all less than or equal to 0. And this is needed because if you look at the equation here, it says that it's for all the j's. Okay, and therefore I want to make sure that this equation holds for all the k's as I'm changing from 1 to k. So now if you want to have this equation to be true for all the k's, then effectively what we are asking is that we are asking the maximum of all the j's that is still less than or equal to 0. Okay, now why do I want to put a max but not a mean? Well, because you want to make sure that even the worst case, okay, among all these inequalities, even the worst case is still less than or equal to 0. Now how do I construct the worst case? Of course, I can make this value as big as possible. So if even for the biggest value of g, I can still be negative, then I can make sure that this equation will hold for all these scenarios. And therefore, if I want to launch adversarial attack, what do I need to do? Well, I really need to ensure that if I am at class I want to go to class T. Okay, so imagine that this is your decision boundary. Decision boundary, and then your data point here, and then this is your input class, and then you want to go to this point, so you want to travel to here. This is C of T. Now you compute the discriminant value. This is GT of your x. Okay, so this is your x, this is your x0. You evaluate GT of x. This has to be higher than any other classes. So imagine that you have another class here, another class here. So it has to be bigger than Gj of the same x that you're looking at. Okay, so put this x into this equation, into that equation. This G of t has to be bigger than Gj of x and any other j's. And therefore, I want to have this max of Gj minus Gt to be less than or equal to 0. So this tells you a very important constraint about the adversarial attack. If you want your attack to be successful, you do want to ensure that this equation holds. For otherwise, how can you guarantee that you will move from your x0, your class I, to class T? That cannot be guaranteed unless this equation holds. So remember this equation. We're going to use this equation over and over again for the discussions that comes afterwards. Alright, so let me give you some outline of what we are going to do next for the remainder of this lecture and for the coming 2 lectures. So we are going to give you a preview of 3 equivalent forms of adversarial attacks. Now I call them equivalent because you can see that they are coming from the same optimization problem but just written in different ways. The 3 methods, they're called the minimum distance attack, the maximum loss attack, and then the regularization-based attacks. Let me give you a quick 1-sentence summary of what each method means. Mean distance attack means that I am going to minimize the perturbation magnitude while accomplishing the attack objective. So what you're going to see is that I will want to make sure that I can go to the other class. However, the perturbation magnitude or the distance that it has traveled is minimized. This is called the minimum distance attack. I want to minimize the distance that the attack takes to go to a wrong class. The second type of attack is called the maximum loss attack. The loss attack says that I want to make sure that my perturbation is controlled, or in other words, I want to make sure that the distance is controlled. However, I want to maximize my training loss. Now, why do I want to maximize the training loss? Because the way to train well is to minimize the training loss. Now, if you want to make the classifier fail, of course, you want to maximize the training loss. So you want to maximize the loss while ensuring the perturbation is controlled. That is called max loss attack. The third type of attack is called a regularization attack. That is based on the concept of regularization. What we are going to see is that the first 2, they are constraint optimization, and therefore you can easily derive the Lagrangian version of the constraint optimization and turn them into the regularized attack. So we're going to look into this problem. Then we're going to look at the geometry of the attacks to draw a lot of pictures to understand the principle of the attack. Now, we want to focus on the type of classifiers that are linear so that we can draw pictures, we can derive closed form equations, and then we can tell you exactly what is happening in the situation. Then know that this linear classifier is not enough for you to get connected to the literature, and therefore we are going to move from the linear classifiers to all these deep models. Okay, so what you're going to see is that we will start by discussing a lot of linear classifiers. using the things that we have learned so far throughout the semester. For example, using the logistic regression, you move along the separating hyperplane, calculating the distance, using the optimization to get the closed form solution. We will do all these using the linear classifiers. And afterwards, what we are going to do is that we are going to link these linear classifiers to a deep neural networks so that you will appreciate why we are studying all these linear models. So this is a quick summary of the attacks, which I will only highlight the equations. We will go into great details of these equations in the coming 2 lectures. So here, what we want to do is just to tell you overall what are they and intuitively what they are doing. So the first method is called the minimum distance attack. It's the first form of attack, which we will spend a lot of time on this minimum distance attack. Because once you understand the minimum distance attack, you will be able to understand the other 2 attacks very easily. So what is minimum distance attack? Well, as I have described, you want to minimize the perturbation distance. Okay, now what is perturbation distance? The perturbation distance is defined as the traveling that you need to take from x0, your input data point, to your final destination, which ideally it would be attack data point, it would be landing on a different class. And so you're measuring the distance between x and x0. Okay, so imagine that you have this is your decision boundary, this is your x0, and then you have choices. Your choice over here, choices over here, choices over here. Maybe I need to draw something like here. Okay, now you can choose which one would be the attack. Well, you can measure the distance here, here, and there. Then we will say which one would be the minimum distance attack. We certainly will say that this one, because this is the closest point to your input data point, and it is misclassified. Now, in order to make sure that you get misclassified, you also want to put a constraint. What is the constraint? It is the constraint that we just discussed. You want that the discriminant function evaluated in the other class, in the target class, has a discriminant value higher than anyone else in the other classes. And so you want to put a max of the j that equals not equals to the t, and then you want the gt to be higher than everyone else. And so if you can minimize this problem, then you will be able to perturb your data point from x0 to x. Okay, so this is the meaning of minimum distance attack. It is one of the 3 attacks, and we will spend a lot of time discussing why this is a very useful thing to learn. And then we want to see how we can generalize this idea to the deep neural network forms of attacks. The second type of attack is called the maximum loss attack. In this equation, what you will be able to see is that I am switching the objective function and also the constraint compared to the minimum distance attack. Here, the perturbation magnitude is changed to the constraint that I want to up above my perturbation distance. Okay, so what does it mean is that I have a decision boundary, I have a data point, and then I will draw a ball. Okay, this ball, according to this equation, will have a radius of eta. This is 0. I want to draw a ball of radius eta, and all my attack has to be living within this eta ball, and then I want to find a point x such that my objective function is maximized. Now let's look at this objective function. This objective function says that I'm looking at gt minus the max of all the gj's. Now that's just the opposite of what we are trying to do in the previous slide. In the previous slide, you have max minus the g. Here you have gt minus the max. So you ask, why do we want to do that? Well, just recall that gt is the discriminant value in the target class. Okay, so this is your target class, this is your input class. So you look at the target class, you want the discriminant value here to be as big as possible, that is bigger than whatever you can find from the rest of the class. And so in this diagram, what do you want to do? Well, you want to go to you want to go to this point. Well, of course, you want to travel to here. This is as high as possible as far as this class CT is concerned, and then it's within the eta ball, and then you want to travel from one point to another. Okay, so this is called the maximum loss attack, and this is just the reciprocal of the minimum distance attack in terms of the optimization formulation. And you can see that because of the geometry, they have two different meanings. One says that I want to minimize my perturbation magnitude while I got misclassified, and therefore you will hit the decision boundary. The other one says that I first draw you a ball, and then I want to travel across to a point which can maximize the loss. So now, given these two formulations, you can quickly imagine that what will happen next, which is to turn these constraint optimizations into an unconstrained optimization, which is now called the regularization-based attack. Instead of having a constraint, I define a Lagrange multiplier, or I call it the penalty parameter lambda, and then I put my constraint into the objective function. And so it becomes a penalized optimization. So this is really the same as the previous two forms of attacks. If you have chosen the right pair of lambda, eta, and epsilon, okay? So this comment is very important if you try to recall from the beginning of our lecture. Of course, we say that by choosing the right choice of epsilon, eta, and lambda, the solution of these problems are equivalently the same. So now for the remaining slides, what I want to do is to quickly talk about the geometry of these objective functions and also the constraints. The objective function, you can see that, let's look at the minimum distance attack as the example. The objective function says that I want to minimize the perturbation distance, and it really depends on what norm that you're using. If you're using an L infinity norm, then what you're doing is that you want to draw all these rectangles. If you use a 1 norm, you draw the diamonds. If you use the 2 norm, you draw all the circles. And so you're really trying to say that if this is my decision boundary, I want to draw the circle as little as possible. I want to use the smallest circle such that I can go across the class. Now, that would be a little bit different if you use, even if you use the same decision boundary. If you try to use the L1 ball, then you can see that the solution will certainly look different compared to the L2 ball case. Okay? So the objective function, the type of norm that you choose, will determine what kind of attack that you will launch eventually. The constraint sets in the minimum distance attack form is, of course, just the set that contains all the x, such that all these k equations, they are less than or equals to 0. And so if effectively what you can do is that if you want to replace the max by xi, where xi is is the index, such that this is the smallest, then just bear in mind that this xi has to be, this I star has to be a function of x. So once you change the data point x, this I star has to be changed as well. In other words, what I want to say is that you cannot just look at all these classes and then determine one k and say that I'm going to fix myself to the k. It's because when you try to solve the optimization problem, this x is your optimization variable, and normally you will run into an iterative algorithm to update your x. So whenever you update the x, the maximum guy will change from one to another, and therefore you cannot just say that I think I should always choose G1 because in my current setting, in my input data point G1, 1 is the class that I will live on. It's the worst case class. But since you're doing optimization algorithm, you're running iterative methods, the x will change, and therefore your I star will also change. And so when you try to replace this in k equations by just one equation, bear in mind that it has to be, this I star has to be a function of x. There's a very simple geometry about this constraint set. Let's say here, this is your target class and this is your input class. What you want to do is that you want to move from one data point, one class to another class. And so it really depends on the geometry of the decision boundary. But essentially, what you're doing is that let's say you're using a 2-norm ball, then you're trying to travel from one point to another with the minimum L2 distance. If we restrict ourselves to the linear classifiers, then our lives are a lot easier. In this case, we will be able to calculate a closed form equation. So before we do the closed form discussion, let's just try to write down all the equations for the linear case. That should be pretty straightforward. In the linear case, the discriminant function is taking this form, where gi equals to w transpose x plus the offset w0. Now, I also put the I here to denote that I'm working on the ith class, because for each class you have a different wave vector, you have a different offset value. And so the decision boundary is determined by the difference between I and t. Okay, so what is gx? Gx is equal to gi of x minus gt of x. Okay, so if you want to compare, this is your Ci, this is your Ct, then this discriminant function gx equals to 0, it will be given by this gi minus gt. That will be your decision boundary, and then that will be your discriminant function. Okay, so now if you write out all these discriminant functions, then you can see that if I enumerate over all the i's, I will have a set of linear equations, except for one. The one that I'm skipping would be would be wt, because the wt is already, it has to be equal to 0 anyway. Okay, and so I'm going to work on this set of equations. And now you look at all these w's, they are defined by your classifier, and so the w's, they are already known to you. They are no longer the optimization variables. The variable that you are working on in the adversarial attack is that you want to turn a data point from one class to another, and therefore the optimization variable is your x. And so now you can call this guy as A, you can call this guy as your B, then you will run into this linear equation. It will be A transpose X equals to B, less than equals to B. Okay, so that means what? Well, that means if you have a linear classifier, then the constraint set, here you have this omega, this big omega set. This set can be reduced to a very simple linear inequality, and that's why we will have the hope that we can write down the closed form equations for simple cases. Now, if you have a linear classifier, then the decision boundary will look like this. All the sets, they will give you a convex, okay, a convex set. So for example, here, this is a convex set. Why? Because if you draw any two dots, you draw a line, this line will always live inside the set, and therefore the set is a convex set. And so if you have a linear classifier, the good news is that everything is convex. All the constraint sets, all the regions, they are all convex. Okay, so this omega that is equal to this A transpose X less than B. This is a convex set. Okay? And therefore, if you can show that there's a convex optimization problem, we know that we can plug into CVX and get a solution. Or in addition, we can also say that any local minimum, they will be global. Okay, so attack, what we are going to do is to look at all these linear cases, and then we are going to transit from the linear cases to the deep neural networks. Now, well, we are going to spend most of the time talking about the minimum distance attack, because once you know the minimum distance attack, you'll be able to generalize the idea to other forms of attacks. And so the minimum distance attack takes this form. This is the mean distance attack. So if you look at this minimum distance attack, And then let's assume that we are limiting ourselves to L2 norm. And so the objective function becomes this L2 norm square. And then you look into a linear classifier, and therefore the constraint becomes linear. Then you have a quadratic programming problem. So what we are going to do in the next lecture is to look at this problem. This is a quadratic optimization problem, and then we're going to derive some closed form expressions of the solution. And then after that, you'll be able to see there's an extremely simple geometry that can describe everything using the tools that we have learned so far. And then we're going to generalize this idea to deep neural network types of attacks. Okay, so to summarize this lecture, we have seen that adversarial attack is a very interesting problem. However, I do want to emphasize once again that the adversarial attack is just one very, very narrowly defined problem in the big literature on robust machine learning. It is interesting because it does attract many attention in the security area, and it does cause a lot of questions about how well can we develop machine learning that is robust against different type of situations. That's a very interesting problem, and that's why we are looking into this problem. And so within this narrow scope, we're going to look at how are we going to form the adversarial attack, not from the perspective of a scattered set of different forms of attacks, but try to come up with a single principle that can understand all these attacks together. And this is in the form of optimization. So we're going to look at these three forms of optimization, and we want to see that there isn't anything, there is really nothing too magical behind the adversarial attack. Okay, once you understand the principle, and once you understand how do you translate from the linear model to the deep neural network models, you will be able to understand all kinds of adversarial attacks. We will learn all these basic principles, and then afterwards, after the next two lectures, we're going to talk about how are we going to defend these attacks. And I hope that after these three lectures, you will have a whole picture of adversarial attack. It can be formulated in certain ways, and it can be defended in certain ways. And I want to give you some personal perspective of how do we look at the subject of adversarial attack. All right, so that's the end of this lecture. I want to see you next time on the internet. Thank you.